My name is Katie, and I'm in the 7th grade. Today I want to talk about energy, nuclear energy to be specific. Oh, and this is my dog Casey. You might see her in the video from time to time because she has a lot of energy to burn.
Following the Fukushima reactor meltdowns in Japan, now many people are rethinking nuclear energy. Maybe it's too dangerous! But I'm thinking, is there a way to make it safer? Why use nuclear power anyway? Well, nuclear power has a very high energy density.
What does high energy density mean? A very small amount will produce a whole lot of energy. Let's look at different types of energy. There's kid-powered energy, good for having fun, even transportation. But it can't power a city.
There's wind power, which is very cool and green, but it will take a lot of windmills to power a city. Wind energy just isn't very dense. Then there's the carbon-hydrogen bond. Fossil fuels such as petroleum and natural gas have a lot of CH bonds. When burned, a large amount of energy is released. Fossil fuels have a higher energy density than wind. Now, nuclear energy has 1,000,000 times the energy density of CH bonds. Wow! Reactors today are high-pressure, water-cooled, solid fuel reactors. They use uranium-235, which fissions to krypton and barium and other products, releasing energy. Loss of coolant leads to accidents like Three Mile Island and Fukushima. In the 1950s, Alvin Weinberg, director of Oak Ridge National Labs, was tasked with building a nuclear reactor for an airplane. The constraints were safe, simple, low pressure. Sounds like what we're looking for! And so the molten salt reactor was developed. After running for 4 years, it was dropped in favor of solid fuel reactors. Today we learned we can run this type of reactor on thorium. In the thorium fuel cycle, thorium-232 transmutes to thorium-233 when it is bombarded with a neutron. Thorium-233 then beta decays, where a neutron turns into a proton and an electron and antineutrino are released, into protactinium-233. Protactinium-233 then beta decays to uranium-233. When uranium-233 is bombarded with a neutron, it fissions, releasing fission products, energy, and neutrons. One of these neutrons hits the thorium-232 atom, starting the process all over again. This is an animation I wrote of the thorium fuel cycle using the Java language in the Greenfoot environment. A neutron hits the uranium-233 atom, causing it to fission, releasing fission products, energy, and neutrons. The neutron hits the thorium-232, causing it to transmute to thorium-233. Then thorium-233 beta decays, releasing an electron and an antineutrino into protactinium-233. Then protactinium-233 beta decays into uranium-233, starting the process again. A molten salt reactor with thorium as the fuel is LFTR, a liquid fluoride thorium reactor. This is the fuel salt core consisting of uranium-233, and this is the fertile salt blanket with thorium. This is this hot salt that goes to the power generator and heat exchanger. This is the warm salt coming back. The fuel salt can be extracted using a simple chemical process to extract useful fission byproducts, waste, and extract the uranium to be put back into the fuel. And the fertile salt can be extracted in much the same way. And you can take the uranium out of the fertile salt and put it back into the fuel salt. This is a freeze plug cooled by an external cooling fan. In the event of loss of power to the reactor, the freeze plug will melt and the fuel salt will drain into a drain tank where fission is impossible. LFTR has many safety advantages over the solid fuel reactor. LFTR has stable, self-regulating reactions compared to the solid fuel reactor, which has unstable reactions, which require active control. The LFTR can run at low pressure compared to the solid fuel reactor, which requires high pressure. There is no coolant needed for the LFTR. Loss of power causes the molten material to safely cool to a stable form. There is no concept of a meltdown. In the solid fuel reactor, coolant is required. Loss of power leads to dangerous overheating and potential radioactive contamination. In the LFTR, the liquid fuel forms ionic bonds with the salt, and they are not damaged during irradiation. The fuel efficiency is 96%. Compared to the solid fuel reactor, which forms covalent bonds, which are damaged during irradiation. The fuel efficiency is less than 1%, and spent fuel pools require cooling. In the lifter, there is no water present. If flooding should occur, the radioactive materials, which are ionically bonded with the fluoride salt, are not water-soluble. There is no radioactive cloud or groundwater. Compared to the solid fuel reactor, which uses water as a coolant. During an accident, it covalently combines with the radioactive materials and leads to widespread release. In the lifter, there is a very small amount of radioactive waste, compared to the solid fuel reactor, which produces large amounts of radioactive waste, which cannot be reused. In the lifter, there is no hydrogen gas, compared to the solid fuel reactor, which contains hydrogen gas that may cause explosions during an accident.
What's next? I'm currently writing a computer simulation to compare the safety of solid fuel uranium reactors to the lifter. So the next time someone talks about nuclear energy, tell them about the liquid fluoride thorium reactor. Bye! Hi! I'm Katie, and this is my dog Casey. I'm back to talk more about nuclear energy. Today, I wanted to discuss the results of the computer simulation that I performed to model the behavior of both the solid fuel uranium reactor and the lifter.
Let's review first. Recall that reactors today are solid fuel, high-pressure, light water reactors. They have many safety issues and concerns, which I detailed in my previous video. The proposed reactor is the lifter, the liquid fluoride thorium reactor that uses thorium as the fuel. This is a block diagram of the lifter. Lifter has many safety advantages over the solid fuel reactor, which I explained in my previous video. I already have a qualitative analysis of the safety issues of both the solid fuel uranium reactor and the lifter. I also wanted to perform a quantitative analysis of the reactor's behaviors under a loss of power fall. So, I created a computer simulation using the Python programming language to simulate both the solid fuel uranium reactors and the lifter's behaviors under a loss of power fall condition. I constructed two state machines for each reactor. This state machine is for the solid fuel reactor. State machines are, in general, useful tools to help simulate a complex system's behavior. The circles are states that the system could be in, and the arrows represent probabilities of events occurring and moving to the next state. For example, let's say you're in state 0 where you lose power. There is a probability that event 1 could happen, which would lead you to state 1. Lose coolant control. Or there is a probability that event 0 would happen, stable shutdown, which would lead to no release. This is a state machine for the lifter reactor under a loss of power. Notice that all these other states are never encountered. As soon as the lifter loses power, it always has a stable shutdown to no release. I used the Python programming language to implement these two state machines and simulate both reactors' behaviors. I ran the simulation a varying number of times, from 100 to 10 million, and these are pie charts of the results I got for 10 million runs for both the solid fuel reactor and the lifter reactor. Let's look at the solid fuel results. Green means no release. There is an approximately 80% chance of that with the solid fuel reactor. Tan means widespread release, approximately 10% chance. Blue means local release. There's a 3% chance, and red means uncontrolled wide release. There's an approximately 6% chance of that. Now let's look at the lifter reactor. Look, 100% no release. Superior safety. Here is a bar chart containing my simulation results for both the solid fuel uranium reactor and the lifter for 10 million runs of the computer simulation. Yellow is the solid fuel, blue is the lifter. Notice that the solid fuel reactor has an 80% chance of no release. Other probabilities include local release, 3%, widespread release, 10%, and uncontrolled wide release, 6%. Now notice that the lifter has a 100% chance of no release and a 0% chance of any of the other probabilities. To conclude then, my simulation results show that the lifter is much safer than the solid fuel uranium reactor under a loss of power fall condition. During my simulation, I made reasonable assumptions for the probabilities of the state transitions in my state machine diagram. If real-life failure rate data could be obtained, I could input it into my program and I would be excited to see the results. Other areas of future work would include simulating other types of faults, such as leaks of pipes and equipment, earthquakes, and other natural disasters.
Well, now I've shown with both a qualitative analysis comparing safety and a quantitative analysis with my computer simulation results that nuclear energy can be much safer with the lifters, the next generation reactor utilizing the thorium fuel cycle. So remember, the next time someone talks about nuclear energy, tell them about the liquid fluoride thorium reactor. Bye! Hi, I'm Katie, and this is my dog Casey. I'm back again to talk more about nuclear energy. Today I wanted to talk about thorium and how it has many advantages over uranium-235 as fuel for nuclear power plants.
When we artificially create nuclear energy, we use the process of fission, which splits apart one nucleus into two different atomic nuclei. However, only 3 elements are easily fissile: uranium-235, uranium-233, and plutonium-239. Uranium-235 exists in less than 1% of the Earth's crust, and uranium-233, plutonium-239 exists only when created in nuclear reactors. Solid fuel reactors utilize low-enriched uranium, which is 95% uranium-238 and 5% uranium-235. A big concern of today's approach to nuclear power is the large amount of transuranic waste produced by the solid fuel. What are transuranics? Let's look at the periodic table. Uranium, with an atomic number of 92, is the last naturally occurring element. Transuranics are all elements with an atomic number higher than uranium on the periodic table, which are created in nuclear reactors. Now let's discuss thorium. Looking at the periodic table, thorium has an atomic number of 90. The lifter uses the thorium fuel cycle. Let's talk more about the safety advantages of the thorium fuel cycle. Fewer transuranics are produced. One of the few that it does produce is neptunium-237, which transmutes to plutonium-238. Plutonium-238 is a useful, non-weapon grade isotope of plutonium that is required by NASA for its deep space missions. This chart shows thorium transuranic production versus uranium-238 transuranic production. Thorium starts the energy generation process 5 neutron absorptions away from the first transuranic produced. Thorium-232, which begins a cycle, absorbs a neutron to become protactinium-233. Protactinium beta decays in 27 days to uranium-233. When uranium-233 is hit by a neutron, there's a 90% chance that it will fission and a 10% chance that it will absorb the neutron. If it does, it becomes uranium-234, which absorbs 1 neutron to become uranium-235. If uranium-235 is hit by a neutron, there is an 80% chance it will fission and a 20% chance it will capture the neutron. If the neutron is captured, then the uranium-235 transitions to uranium-236. When uranium-236 absorbs a neutron, then it becomes neptunium-237, which absorbs a neutron to become plutonium-238, which, remember, is a useful non-weapons grade isotope of plutonium that NASA needs for its deep space missions. This is the transuranic production path when we begin with uranium-238. Note that we began with uranium-238 instead of uranium-235. This is because nuclear power plants use low-enriched uranium, which is 95% uranium-238. Uranium-238 absorbs a neutron to become neptunium-239, already the first transuranic. Neptunium-239 beta decays to plutonium-239, weapons-grade plutonium. Plutonium-239 has a 65% chance of fissioning and a 35% chance of capturing a neutron if it is hit by one. If plutonium-239 captures the neutron, then it becomes plutonium-240, which absorbs a neutron to become plutonium-241. Plutonium-241 has a 75% chance of fissioning and a 25% chance of capture. If plutonium-241 captures a neutron, then it becomes plutonium-242, which absorbs a neutron to become americium-243 and curium. So, you see that the uranium-238 base path produces many more transuranics than the thorium path.
What do you think, Casey? Fascinating, isn't it?
A second safety advantage of the thorium fuel cycle is that when thorium is used in a fluid form, the fission products are easily removed safely and utilized, such as technetium-99, which is a corrosion inhibitor, molybdenum-99, which has medical uses, krypton, xenon, ruthenium, rhodium, and others, and rare earths, such as lanthanides and yttrium. Here is a block diagram of the lifter. This is the fuel salt core with uranium-233, and this is the fertile salt blanket containing thorium. Now note, here is where the fission products can be easily extracted from the fuel because it is a liquid, and the useful byproducts can be taken out.
Wouldn't it be great to get all these useful byproducts while at the same time generating power?
There's a very low risk of nuclear proliferation because the uranium-233 is inevitably contaminated with uranium-232, giving it a very high gamma radiation and making it almost impossible to transport away and try to make a bomb out of. Although not necessarily a safety advantage, another advantage to the thorium fuel cycle is that thorium is highly abundant in the Earth's crust. This is a table showing various elements and their abundance in the Earth's crust. Note that thorium at 10 parts per million is much more abundant than uranium-235 at 0.018 parts per million. This figure compares and contrasts the quantity of radioactive waste in a conventional solid fuel reactor with the lifter. This shows the input and output for 1 gigawatt year of electrical energy. This is the fuel input for both the solid fuel uranium reactor and the lifter. This is the beneficial use for both, and this is the waste output for both. Note that for the solid fuel uranium reactor, you need to enrich 35 tons of uranium from 250 tons of raw uranium, put this in the reactor, and this generates 35 tons of long-lived radioactive waste that lasts for 10,000 years. These are all transuranics. It also produces 250 tons of depleted uranium, which is also waste. For the lifter, you only need to start with 1 ton of thorium, and you put all of this in the reactor/generator, and it produces 0.83 tons of useful byproducts. For example, medical molybdenum-99, bismuth-213, and others. It also only produces 0.17 tons of medium-lived radioactive waste that lasts for less than 300 years. So, we can see that the solid fuel uranium reactor takes a large amount of fuel and produces a large amount of waste, while the lifter, being more efficient, only takes a small amount of fuel and produces an even smaller amount of waste, with useful byproducts as well.
Casey, what's that you're playing with?
You know that if this was thorium, we'd have a lifetime supply!
So I think we could conclude that the lifter has many advantages over the solid fuel, high-pressure, light water reactors of today. Lifter has many safety advantages, is much more efficient, and produces much less radioactive waste. So remember, the next time someone talks about nuclear energy, tell them about the liquid fluoride thorium reactor. Bye!